cambios de última hora, pero esperemos que todo vaya funcionando. Bien, esta escuela es organizada en la idea original por el Instituto Avanzado de Cosmología, pero después se sumaron todas estas instituciones que ven la División de Astronomía de la Sociedad Mexicana de Física, lo que debemos de hacer y luego ya después escuchar a los expertos del mundo hablar de simulaciones. DESI es un proyecto de un telescopio en el cual hay algunos mexicanos involucrados. DESI México está apoyando este proyecto, esta preescuela y escuela, y el Instituto Avanzado de Cosmología, que como algunos de ustedes saben, han participado en algunos eventos. El Instituto Avanzado de Cosmología promueve este tipo de reuniones muy académicas, muy científicas, de alto nivel, para justamente tener una nueva generación de personas como ustedes que se involucren en cosas de investigación de alto nivel y vinculados a investigadores mexicanos y del extranjero. De hecho, esta escuela tiene la idea de generar como un primer frente de onda de simuladores cosmológicos en México. Ya hay algunas personas que lo hacen, pero son personas, profesores, y la idea es que los jóvenes se genere una nueva camada de gente como ustedes que empiece a hacer simulaciones cosmológicas en México. Entonces, esta escuela tiene ese objetivo. Vamos a ser muchas personas, y esperemos que una buena parte de ustedes se interese por esto, haga investigación en esto y se vincule de una manera entonces muy directa a todos los aspectos numéricos de las simulaciones, que como van a ver no solo es correr un programa, hay muchas cosas de análisis, de entender teoría también, etcétera, etcétera. Bien, entonces el objetivo es ese, esperaremos que le echen muchas ganas. Algo muy importante va a ser, y no es precisamente para ustedes, es la puntualidad. Vamos a tener un programa muy lleno y necesitamos empezar a tiempo en los siguientes días. Hoy era la llegada, las maletas, etcétera. Empezamos un poquito tarde por eso, pero vamos a ser muy estrictos con el tiempo, y dado que estamos haciendo un gran esfuerzo económico también les pedimos que pongan de su parte, si estén a tiempo en todas las sesiones, y le echen ganas con los ejercicios. Esa parte es muy importante, es algo que hemos promovido siempre en el IAC, no hacer ahí eventos ahí como salgan, no hacerlos bien, y vamos a darle seguimiento a las personas para que si tienen algún problema, bueno, que lo puedan resolver, ¿no? Bien, sin más, doy la palabra a quien va a moderar. Gustavo va a ser el encargado de moderar en la mañana, no sé cuál sea el siguiente, y bueno, bienvenidos, gracias.
Bueno, bienvenidos. Entiendo que tenemos participantes de habla inglesa, entonces a partir de ahora vamos a cambiar a inglés. So welcome you all. And I believe the first speaker will be Mariana. Just before that, let me make you an announcement. So we'll be uploading more instructions about software and about the courses of this preschool on the website. And also, as a suggestion, we will have a blog. So you can actually write questions there, and hopefully Mario, Octavio, and Julio can write answers there as soon as they see them. So, well, let's start. So Mariana will be the first speaker, and she will give you a broad overview of the subject.
Tom? Perfecto. So I'm going to start giving some logistic information. This is the program for today. As you can see, it's very short, so please be on time for tomorrow. I'm going to give some information for today. We have a lunch at 1:30 to 50. we are providing this lunch, so you have some tickets in your gafete. So you will have to go to Odontología. That is not that close from here, but you have several local people that are gonna guide you to this place. It's 20 minutes walk from here. So please get close to these local people so that you can get all together to this place. You have only 1 hour and a half to eat, I think. Yeah, I think only 1 hour and a half, so you have to be very fast in this transportation to this place. This is a program for tomorrow. Again, a call of attention. You need to be on time at 9 because the same lecture is going to be always at 9. So you are going to lose a lot of information if you don't arrive on time. And this is some, we are providing 2 lunch. The first day of the school next week and the last day. The other 2 days you have free lunch, so you need to look for a place to eat. And there are a few places. If you are not from here, you can ask local people for these places and you can take lunch in those places. You have 2 hours for it next week. For those that are fellows, and they are in this Hotel Lisboa from today, so you need to be there sometime at the evening to do the check-in. And if you are leaving before the end of the school, please tell us so we can spend less money on this. If you have some problems, we will have another registration desk only another day on Monday. But if you need the tickets, go look these people, Oscar, Brendan, and Matthias, to get these tickets. And if you have any problem with the meals or no tickets or whatever, look for Brenda. And if you need to solve something about fellowships, look for Chandrachani, that I don't think is here, but she's going to come later, I think. For the internet, this is the Wi-Fi for this event. So please take a note because I'm not going to pass this again. And this is the password. Check if it works now. If not, tell me or tell any of the other people helping me, and we want to try to solve this. So I'm going to give a few minutes before starting. Gustavo, can you tell me how much time I have? Because I think I have to 20 minutes. 40? Okay. Well, so are you ready? Yes? I will be asking questions during the so please answer because I feel alone. Okay, so I'm gonna start. So this is the, yeah. Any of the local people that is helping, Oscar, Brenda, someone? No? Okay, I'm gonna try to solve it after this talk, okay? Pay attention to this, don't look for the Facebook for this first talk, then you can take. So I'm gonna start talking about simulation and how we use them in cosmology. In particular, I'm gonna focus in galaxy surveys. That has a reason, is because we are pushing a group of observational cosmology based on some collaboration that we are involved, that are eBOSS and DESI. Mostly DESI, we have a big group that we are pushing this, and so this talk is gonna be a kind of presentation of how we use the simulation for doing cosmology. I'm gonna be very fast in many things because I think many of you have already heard me before, but this is like the first phrase that is in the poster. We are preparing you for analyzing these large scale surveys. So that's why the outline of the presentation is gonna be talking a first time of what are these galaxy surveys, and then I'm gonna go directly to give some examples of how we use the simulations to make large-scale structure analysis. I'm going to be talking a lot about eBOSS because it's a finalized survey, so I have done a lot of work on this. Some of the examples are completely straightforward to eBOSS, that is the next generation of surveys, but also they will be directly applicable to the case of DESI, that is a future survey that we are starting now to plan and to prepare everything to be ready to analyze the data when it's going to come. That is going to be in 2018. So we are all involved in this. So for the people that don't know what is a galaxy survey, this is a nice picture that I like to show to people that don't know galaxy surveys. All these points that are in this video are real galaxies that were measured with a spectrometer that is in New Mexico. This is part of eBOSS data that now is public. And you can see how measuring all the spectra of all these points, we are really tracing the matter distribution of the universe, the luminous part of this. And we are trying to extract information about this distribution of matter in the universe. So as you can see, it's very nice to see these filaments and these voids. And this information that we are trying to get from this structure is what we are going to learn how to use simulation to extract this information. So we have many experiments today devoted to explore dark energy problem. So this is an example of all the experiments that are looking for understanding of dark energy. In particular, I'm highlighting the experiments that I already mentioned, that are eBOSS, that already finished to take data, that is here. I don't have the pointer. Well, the pointer is somewhere. Okay. So eBOSS is here. We already finished to take data. The data is already available somewhere. And what we're going to teach you is how we can use the simulation to analyze this data. And you're going to see that we need the simulations in order to extract the information for these galaxy surveys. I'm going to be talking also about other spectroscopic experiments like eBOSS, that is the next, the extension of eBOSS program that is already taking data. We have already 2 years of data. I'm not going to show any plot for eBOSS because it's already ongoing work, but I'm going to be talking of the kind of work that we are doing now here. And finally, I'm going to talk about what is required for DESI, because we would like you to be involved in these projects working on this DESI data. So as you can see here, we have two colors, photometric surveys and a spectroscopic survey. Any of you, all of you knows what is the difference between both of them? This is yes or this is no? Who knows? Okay, very few. So I'm going to be, okay. Before that, I'm going to be talking about this line. This line is separating 2 stages of experiments, so stage 3 and stage 4. This is important because we are just here. We are in the middle of 2 experiments, and we want to see what is the difference between these 2 experiments. So this line is called stage 3 and stage 4 experiment, and it's coming from a review that happened in 2006, where a group of specialists in dark energy meet together to decide what is the future of dark energy and how we are going to do to understand what is dark energy. And then they made a very careful analysis of all the observables that were at that moment robust to understand dark energy. And they make some proposal of how the government of US needs to invest money to understand better the dark energy. And they defined these 4 categories. The stage 3 was all the experiments that at that moment were planned, but they were not started yet. So it was in 2016, stage 3. And the stage 4 were like very long-term experiments that were required to improve at least an order of magnitude in the error of these parameters of the dark energy that we want to learn about. So we are in the border here. We are finishing now all the stage 3 experiments, and we are passing to the stage 4 experiments. So what it means is that here we have some level of understanding of the dark energy, some error on the parameters of the state, of the question state of dark energy, and we're not going to go one order below. We're going to reduce the error bar. So all of cosmology is about now is to reduce all the error bars in many of these things. And why this is important? Because we don't know what is dark energy, and we need to discriminate between a jungle of models that we have today as plausible models for dark energy. So this is our work. And we are using two kinds of surveys, photometric surveys, that are these in blue. We have many examples. We are not involved in any of them. DESI, LSST, Euclid, and WFIRST. And the difference with respect with the spectroscopic surveys is that in this case, we just have information about the flux at different filters. And with this information, we are selecting objects and we are constructing catalogs. And with these catalogs, we are inferring cosmology. We are missing one important information. So we have all the coordinates, angular coordinates of these objects, but we don't have the radial coordinate of this object. So to get this information, we are using special techniques to get the redshift. And this redshift is going to give you this radial coordinate. And as we don't have this information from a real spectra, we have some error on this measurement. So using this chain of data, we can get at the end a photometric survey that will have the positions of all these objects with certain error bar for the photometric redshift. These are the photometric surveys. This is an example of how we can get the redshift using this information of the filters. And that can give you an idea of the way we do with these galaxy surveys. All are different experiments that are using different filters and that can improve the errors in this redshift measurement later on. In comparison with these surveys, we have the spectroscopic surveys where we, in addition to this selection of targets that I was talking before, here, then once we have selected all these subjects, we measure for each of them an spectra. And that means that we are using different techniques like putting some fibers on some plates and looking at the sky and getting the spectra like this. And using this spectra, we are getting this information of the radial coordinate that we need for construct all the structure in three-dimensional case. So going back to this, these are the three experiments that I'm going to be talking. I'm going to start with eBOSS. So we have here eBOSS, the telescope that is taking all this spectra. We have this took data between this 2008 and 2014. And we have 1.2 million of luminous red galaxies. And we have this number of quasars. As you can see, we have different tracers of the matter, and we are using them for extracting cosmological information. The main goal of this experiment was to measure the periodic acoustic oscillation peak to 1% precision at this redshift. We already finished to take data of this survey. And this is the angular mask on the sky. This is the part of the sky that we measured in 2014. And here we have all the papers where all these analyses are together. So if you haven't heard about this, we have different tracers that we can use for doing cosmology. In this case, in this experiment, we are using two tracers, massive galaxies, CMAS galaxies, constant mass galaxies that are luminous red galaxies at this medium redshift, and a sample that is a lower redshift. And we also have a sample for quasars. But this sample of quasar, we cannot use it for doing clustering itself because it's not homogeneous. We are using it like a tracer of the matter between the line of sight and the quasar. Second example is eBOSS. It's an experiment that is now taking data. So we have here what eBOSS did, and this will be the extension of eBOSS. And we have more tracers, because if we are going to look further, we need to look for different tracers of the matter in order to have this information. So in addition to the LRGs that I have been talking before, we have the ELGs, emission line galaxies, and the quasars again, but this time these quasars are constructed in such a way that we can do cosmology with them, because they have been taken in a homogeneous way in the sky, so we can study the clustering properties of these objects. again, as we are using the same instrument and eBOSS, we are expecting the same precision in the measurements. And again, the main goal, the scientific goal, is measure the baryonic acoustic oscillation in this redshift range that is a little bit farther than before. Finally, we have DESI. DESI, as I already said before, is a stage 4 experiment. That means that it's going to improve all these errors in the observables that we are using for study dark energy. We are using everything bigger, a telescope bigger, more degrees in the sky, more fevers, more spectrographs, more everything. The tracers that we are using are very similar to eBOSS. So we are using these LRGs that we have been using in eBOSS. We have these ELGs that we are using now in eBOSS. This quasar that we are also using in eBOSS, and this other quasar that are helping us to trace the matter between the quasar and in the direction of the line of sight. So we have these 4 different tracers that are giving us information of different ranges of redshift in the sky. So how we can do cosmology with these galaxy surveys, in particular with these spectroscopy surveys? So we can do many things. So we have all this range of possible analysis that we can do. So we can explore distance, and with that we are going to study the expansion history of the universe, and with that we are going to learn something about dark energy. We can study the structure, how the structure is formed, and it's going to give us information about the density, energy in general, and the gravity. And then we can do other stuff, just looking at the clustering of galaxies or the full shape of the power spectrum, as we're going to see, or combining it with other information, as the CMB, to extract all this information about other cosmological topics, like density of energy, inflation, etc. So we're going to concentrate in these 2, because we are, as you're going to see, the main goals, the scientific goals of all these experiments are based or are in 2 observables that are the baryonic acoustic oscillation of the redshift space distortions. So this is our next slide that's going to tell us these different ways of exploring dark energy. And as I already said, we have all these ways. All of them are going to be explored in different experiments, or even in the same experiment with these future surveys, even spectroscopic or photometric. But for a spectroscopic case, the spectroscopic experiments are optimized to get information about these 2, baryonic acoustic oscillation and redshift space distortions. So I was not planned to explain again baryonic acoustic oscillation and redshift space distortion, only if there is a lot of people that don't know what they are. Do you know what they are? You know. Who don't know what they are? Everybody knows. I'm surprised.
Maybe you may mention something.
I'm going to mention very briefly. So I'm going to start with the baryonic acoustic oscillation. So this film is a picture, a cartoon picture of what they are. So the idea is that in the early universe, in each of the upper densities, the competition between gravitational collapse and radiation pressure generates this pressure wave that starts propagating from this initial perturbation until the decoupling time. At the decoupling time, it gets frozen, and then this imprints a characteristic scale in the matter distribution of the universe. That happens in every single upper density. What it means is that this signature, this particular scale, is going to be printed in a statistic way in the universe. What happened is that in these upper densities will be formed all the galaxies. So we can look for this signature in the distribution of galaxies. And if we study and we use statistical tools as the correlation function that I'm going to explain in 2 slides you're going to find this feature as a peak in the two-point correlation function. That is going to tell us some information about the clustering that had certain characteristic scale. That is the BO scale. So this was the first detection in one-dimensional, but if we explore this signature in two-dimension, this is the two-point correlation functions in two-dimension, we are going to see that the objects are very clustered, but then the BO peak is this ring that is saying that this is a particular scale that we are going to find the galaxies are separated by, just because this phenomena of baryonic acoustic oscillations. So we can use this particular scale for studying the expansion history of the universe, because we know how to compute this acoustic scale, and we can measure it using these galaxy surveys at different times, at different redshifts. So that's going to give you some information about the expansion history of the universe. In particular, if we measure this separating the line of sight direction and the transversal direction, we can explore two different distances, the angular distance and the Hubble parameter, and the dependency of them on the cosmological parameters are different, so they are giving us information about the cosmology that is in our universe just using this information. The second observable are the redshift space distortion, and the idea is that we are observing all these galaxies. And as I already told you, the information of the radial distribution is coming from the redshift. So the problem is that these redshifts have different sources of information. Is this recession because of the expansion of the universe, and also they have the peculiar velocities because these objects are falling in the potentials. So what happened is that the original objects that are here are going to appear to us like clustered in this direction, because of this measurement of the redshift space instead of the radial coordinate. So what it's going to give us is some distortion in the two-point correlation function. So what is going to happen is that if we really could measure this radial direction, we're going to see this two-point correlation function that is completely symmetric. So we have the ring here and the center. And what we really measure in real life is this, because we have this effect of the redshift space distortion. And this pattern is giving you important information because it encodes all the velocity information, and it's going to give you information about the growth factor that is defined as this. So why the growth factor is important? Because in different cosmologies, the structure grows differently. So if we can measure this growth factor as a function of time, we can constrain cosmology with that. So that is the idea. So where we are in that? We have these two observables. We have this experiment that's already finished to take data. So we are here now. eBOSS finished this summer to publish the final analysis using galaxies, 2016. And we have these points. And these points are summarizing all the information that we have up to now, combining with all the observables that we can use to constrain cosmology. And we have these points here that are the distance as a function of the redshift. And we can distinguish, using this measurement, between different cosmologies, because different cosmology is going to have different behaviors in this plot. So if we have these points, we can find what is the best model that describes our data. This is, in the case of distant measurements, if we are using the information of the growth factor, we will have these measurements of the growth factor as a function of the redshift. And we will have all these points. And using these points and different models, we can constrain cosmology, and we can also constrain gravity using these growth factor measurements. So this is where we are. These are the error bars of our data. And I already told that the next step for all these experiments is to take the same measurements at different redshifts maybe, but reducing the error bar. This is what it's all about. But this little thing is very, very complicated. And this is the main work of all the observational cosmology today. So we are here. We will be here with eBOSS, and we will be here with DESI. And our goal will be to reduce as much as possible these error bars and to trace all this redshift range And with that, we will be able to discriminate between all these different cosmological models. So this is the reduction of the error bar that we expect to have with these new experiments. So we are here. This is percentage error. And we want to be here, 1 order of magnitude below. This is the same plot. What is the difference with this? Well, it's the same information. We have also other experiments that are trying to do the same thing using different experiments, like here. But these are those that we are interested to highlight, at least for this talk today. At the same time, we want to do the same for the growth factor. We have these measurements today, and this will be the points for eBOSS, expected points for eBOSS. And then we will have what we expect to have for DESI. And at the end, we are going to be able to discriminate between all these possibilities of cosmological models. But that is the idea, and the main goal of all this experiment is going to be this single plot that is constraining the parameters of the dark energy in order to constrain the space parameters to understand a little bit more about this. So we have how these contours are expected to shrink with time with the different experiments and the scales of time. So we are here, and we are preparing you to work on this if you are interested. So how we do that? We use large-scale structure measurements. For that, I think I'm going to skip all the statistical description because I don't have time. How much time I have? 10 minutos. Yes. To go to the other, I'm just going to be very fast. So the statistical description of this distribution of galaxies is using this definition of fluctuation of the density, contrast of density. What we use as our variable is the density, the fluctuation around the mean density. This is our observable. And we are modeling this like an stochastic process. So for describing an stochastic process, what we need to determine is this probability distribution. And this probability distribution is completely specified by the moments of the distribution. How many of these moments we need to describe? It depends on the kind of random field that we are using. In particular, if we have a random Gaussian field, it is completely specified by the 2-point statistics, like the second moment. But if the field is not random, like this, we will need more than the 2-point, the higher order point statistics. So this is just saying that for a Gaussian random field, it's completely specified by this 2-point correlation function. And we expect that we have some reasons to think that our distribution are very close to a Gaussian process. So our first step is to use this 2-point correlation function that is defined as this. So this is a maybe not very straightforward definition if you see like that. So I'm going to be giving like the interpretation, probabilistic interpretation. So if we have two volumes separated by a distance r, the correlation function gives us the information about the probability to find a galaxy here and a galaxy here when this is the distance of separation of the two volumes. So if this field was completely random, the correlation function will be 0, and the probability will be given only by this expression without this term of the correlation function. So what is telling us this 2-point correlation function is something about the clustering of matter in the universe. So this is for a continuous process, the last definition. The real definition for a punctual process is this. We have different kind of estimators. This is one of the estimators of the 2-point correlation function. And what we do is to compare a completely random distribution with a distribution that we are measuring if they are clustered or not, and then compare the distribution of the pairs of distance of these different objects. And in such a way, we can have an estimator of the 2-point correlation function. I skip this, but we have similar definition by the higher orders correlation functions. And I already said, we think that it's pretty close to Gaussian, but it's not completely Gaussian. We need to explore also this two-point correlation function, the higher order correlation function. So how we do that with large-scale surveys, in this large-scale analysis in galaxy surveys, we have all these steps, and in all these steps we need simulations. So we start with the observation, we define sub-targets, we define some systematics that are related with observations. All these also require simulations, but then after we need to define our observable, redshift space distortion, VRO, others, whatever. And then we are going to combine the theory, we're going to combine the simulations, and we are going to try to combine all this information to infer some cosmological parameters. So a particular example of a VRO, so to put this in a less abstract way, I'm going to focus in this part how we do simulation in these parts for doing this task. So simulations are basically used for two purposes at this point. We have the simulations. We don't need very precise simulation for this, but we need certain accuracy in order to guarantee that we have the accuracy of the observables. We use it to test methodology and to compute covariances. In both examples, for example, in the last analysis, we generated a set of mock catalogs that are not really simulation that you are going to hear about the next week, but this is what we need up to now, given the precision that we have. And these simulations, what they have is that they reproduce the statistical properties that I already talked about before. So if they are not really moving particles like we are going to do next week, following the equations, but we can generate them in such a way that they have the right properties of the statistical properties that we need for them. With these simulations, we can explore the different observables, the different estimators, two-point correlation function, power spectrum, two-point correlation function, B spectrum, etc., etc. We are going to test our methodology with these simulations. So, for example, here we have all these error bars are given for all the variance of applying the same methodology to a set of 1,000 mocks. And then this is verifying that we can extract the information. If we mimic the universe and we give the statistical properties that we need, and then we extract the information of these mocks, that guarantees that we are really, we have a robust technique for extracting information. So this is the idea. This is the power spectrum on the top, etc. Two-point correlation function, monopole, quadrupole, etc. This is just testing how the estimator behaves for different realization. It's taking into account different sources of error, but we can also test our methodology to guarantee some precision on the measurements of the angular diameter distance and the Hubble parameter. And this is also just an example. When we are trying to fit any observable, we have something like this. We have some measurement, that are these error bars, this point with these error bars. We have some template, some model, and we are going to try to fit the best model to this data. So this is a particular technique, but the idea is that if we apply this methodology for all the mocks, we are going to have a bunch of points like this, and this will be the data. So what is telling us this kind of test that we are doing with the simulation is that we are capable to extract the information, performing the analysis as we are doing in the mock catalogs. And that is giving us some guarantee that this measurement that we are doing with real data has certain range or error bar. The second purpose of this simulation is estimating of the errors that are associated to these simulations. So for doing all these feats, we need to have some errors associated to the estimators. So, for example, here we are using different kind of simulations, more precise than before, just for measuring what is the bias in our measurement, just for applying our methodology to these mock catalogs. And that will give us the systematic error that we associate with our measurement, in addition to the statistical error that is also given by these simulations. So in general, we're going to be doing a lot of this stuff in many of the variants. And one ingredient that you are going to hear about, I hope, next week, is a key ingredient that we need to compute with this simulation is the covariance matrix that is giving us the error that we are going to use for fitting all this data that we are using. We can also study what is the covariance between the different parameters that we infer for the different measurements. For example, here we measured the same, we're using the same data, but using different methodologies, the same parameters, and we are studying what is the covariance of the different parameters that in real life, in theory, should be zero because they are analyzing the same set of data, but using different methodologies. Okay, but given the systematical errors, the observational errors, whatever, they are giving us, in fact, in real life, complementary information. So the only way that we have for having this information is using simulations. So the main challenge is that for now, given our precision, we don't need to go too far for the simulations. We have some precision, so we need some precision for the simulations. For the future, is not longer true. We need to reduce the error bar in everything. So one of the things that we need to have is better simulations. Simulations that have more information about the mid-nonlinear regime that up to now we are not really considering. I really don't have time to this, but this is what you are going to learn. So anyways, it's okay. The third utility of this simulation is to explore this nonlinear evolution. We know that the growth factor is a highly nonlinear process. So we know how to describe pretty well the linear regime, but we don't know how to describe the nonlinear regime. So the only way that we have to address this part when the constant of density is very close to 1 is to use simulations. So we have these different ways of extracting this nonlinear information, and this is also a particular example of the baryonic acoustic oscillation. These oscillations are representing the baryonic acoustic oscillation. As you can see, all this is the linear behavior, and this is what we have in the nonlinear behavior. And this line that is with these error bars is coming from simulations. The only way that we have to address the nonlinear regime is up to now using simulations. So these are some approximations that are using perturbation theory. We can have different ways of doing perturbation theory, and we will have different kinds of approximation. But up to now, what we use like our truth for the nonlinear regime, at least, is this coming from simulations. So this is just to giving you a flavor, and I finish with this. It's 2 minutes. In DESI, what we are doing now is that we know what we want to measure. We know what precision we need to have. We know what are the precision we have now. We know where the errors are. We know how much is coming from the systematic, how much is coming for astrophysics, how coming for the, etc., for the model. So we need to reduce everything. And the way to address this is using simulations. In particular, for example, the baryonic acoustic oscillation, we need to have this level of precision in the measurements, and for that we need to take into account these nonlinear effects. We need to compute all this covariance, and we need to generate more than 1,000 mocks that we have today. we need to explore all the imaging systematics, and we need to use simulations for understanding what is the effect of all different systematics that we have and how this is affecting our estimator of the observables. And with this I finish. I have the same for the redshift spare distortions, and these are the kind of simulation that we need to generate for DESI, for different science cases that I already talked about. This is the starting point. This is the simulation that we have now. And we need to go further than that. So you're going to have this presentation later, but we have all the simulations now, and this is just the first step. We need to improve everything. This is the case of the non-standard models where we are now. So all this is the starting point, and for the future we need to do all this in better. So I hope you participate in this. I finish with that. Thanks.
Thank you, Mariana. Are there any questions? Comments?
Everybody understood everything?
Well, if not, we move to the next speaker, who is Mario, and he will be introducing us to M-body simulations.
Ahorita lo voy a buscar. Mientras te doy la del Instituto de Física, ¿no? Ajá. Ta, ta, ta.
Bueno, se escucha. Y el enchufe. Mariana.
Allá. Toma. No venga a poner el cargador. No te vayas a hacer nada.
Ya me estaba en...
¿La vas a especificar un poco?
¿Está listo?
Espérame.
Okay, so we will start with Mario.
Okay, it's my turn to talk about the introduction to M-body simulation. the contents will be this one. I will make an introduction to see what we have in the universe, galaxies and structures. Then computational physics, in particular numerical cosmology. Then using some simple numerical codes. The most simple is this one, the N-body N2. Then I will present the N-body problem and the structure of the codes, how they will build, and then present an example on globular cluster dynamics, talk about Monte Carlo and initial condition, other simulation, the SPH to deal with the hydrodynamic part of the systems, and then the large scale structure formation in the universe, and then some projects. This is an ad. If you want to know very nicely the problem on numerical physics, in particular in astrophysics, you have to read these two books. So, okay, so the first one is to make an introduction to the problem. So, okay, so fields that matter in galaxies, general relativity, Boltzmann equation and N-body methods, and construction of galaxies. In the universe, we have a lot of kind of galaxies. We have Andromeda, the Sombrero, the Mices, the irregular galaxies, very nice spiral galaxies and antennas, and so on, interacting galaxies, and other kind of galaxies like this one, which has a bar in the center. The classification was given by Hubble. We have three kind of galaxies: spirals with bars, spiral with bars, and ellipticals. And the main thing we have to deal with when studying galaxies is to find, for example, the rotation curves, where we have a lot of observational data. Then general relativity and its Newtonian limit is starting with the Lagrangian, which is basically L equal to or proportional to the scalar Ricci object, and we have that this is a Lagrangian for basically to find the metric of the space-time. By doing the variation, we have the Einstein equation or the field equation, which is the specific equation for or to find the metric. And we have the geometry, and we have the sources, which is energy momentum tensor. So in the case of nonlinear evolution of the universe, we have to deal with perturbation. Basically is to expand the metric. Basically to expand the metric in terms of or around the Minkowski metric, and we have this perturbation. So introducing this perturbation in the field equation, in particular the 0 element, give us the Poisson equation, and this is the Newtonian or so-called Newtonian limit for general relativity. This equation has this solution formally. Instead of differential equation, we have an integral equation. We have the boundary conditions, which are very important when studying some particular systems, and it depends, or the source is the distribution of matter. So this is the problem we have to solve. We have to, or we will see several methods which start with the differential equation, or another method which use the integral expression. If we use the integral expression, then we have that 1 over this r minus rs is the Green function, and it can be expanded in harmonical spheric in general in this way. And we have two terms for the potential, the neutrino potential, which are the internal expansion when we have less than case, or the external case, which is for the greater or involving these terms. So for the internal we have this expansion, and for the external we have this expansion. And so we can arrange all the terms in terms of the momentum of the expansion. For internal are given like this one, and for the external given like this one. In Cartesian we have this expansion, and the force for the internal part is the dipole and quadrupole. If we are just taking or making the sum up to the quadrupole term, L equal 2. And the internal monopoles are given by this one, which is basically the total mass, the dipole, and the quadrupole. And for the external is another term which is here, but basically it's the same, is more or less the same expression. And we have the mass and the dipole term and the quadrupole term. This is basically total mass up to a given radius. Okay, so this is formally the method that we have at hand to make numerical simulations using this expansion. Okay, so the Boltzmann equation and the n-body method specifically. If we have a system with many particles, many stars, for example, then the Boltzmann equation that describes the system is this one. For stars, for example, or galaxies in a cluster of galaxies, they are considered that they are collisionless, so we don't have this term. And the distribution function basically depends on the gravitational part, which is given by the Poisson equation, which I wrote here. And the distribution function for a scheme of n-body, for the n-body problem, can be written in this way, where we have n particles, n stars for example, and then the Boltzmann equation reduced to this one. Basically is the second law, the Newtonian second law. So given n particles with masses mj, we have to advance, the system with this equation. So constructing a galaxy will be in this way. In general, I'm putting here the collisional term, and we have a system of n particles. In the phase space of individual particles will be that n dots or n points in this space is the system. And the evolution of this distribution of particles in the phase space will be given by the Boltzmann equation. In particular, we can construct the Ginius equation, making an integral in velocities or momenta, and we have the field Ginius equation. Basically, is a continuity equation, and if we multiply by the velocity or the momenta and integrate in velocities, we have the second Ginius equation. Is a kind of Euler equation or Navier-Stokes equation with a straight tensor and so on. So this is another way to solve the Boltzmann equation, making a compactification, if we can call in that way. So in general, we have for a galaxy, for example, that a galaxy has a bulge, it has an halo of dark matter, for example, with this profile, the bulge with this profile, and a disk with this profile, which is an axisymmetric system. And what we have as the first problem is to build a model given the bulge with this density profile, then construct numerically, given, for example, 10,000 particles, for example, for the bulge, and then put all of these particles in the Cartesian in the configuration space according to this distribution function. The same for the halo and the same for the disk. And with all of this configuration distribution function, we can construct the configuration space part. But we need also the velocity for each particle. So the simplest case is that the velocities are Gaussian, for example, like this one. And we have an isotropy in the r, phi, and theta in spherical coordinates, for example. If all of these are equal, then we have the isotropy condition. So for this case, we have, or we can use the second Jeans equation to construct an equation for specifically, or to find specifically the data we need here. So we have 3 parameters to construct the velocity of each particle in the spherical coordinate system. So if we have isotropy, for example, that is the simplest case, we have this equality, and we can find then the equation for the velocity dispersion in the radial part. So from here we can obtain this equation, and is given in terms of the density and the force each particle feels. So the distribution we have to deal with is given by this one to find the velocities in the system, and only one parameter. So given 5 numbers, 5 random numbers, and given several distributions, for the velocity will be this one, and for the configuration space will be this, and this one, for the bulge, for the halo, and for the disk. So for constructing, for example, the bulge, we have to give 3 random parameters, and with this distribution construct the position in this, with this, or consistent with this distribution. And then give 3 parameters, and with this distribution of function for the velocities, find the 3 components of the velocity of the particles. So this is the general method. The worst case to deal with is the disk, because of the symmetry. So it's a little bit more complicated, but we use this approximation in which the rotational velocity for a spiral, for example, for spiral galaxies, we have that the dispersion velocities are much less than basically the rotation of the system. So the velocities will have this anisotropy, or this form. It's a Gaussian also, but we have to find 3 parameters for the system, and both of them depend of the position, the radial position in which we are putting a particle, for example. And within this approximation, we will have that. Sorry, here there is a typo. It's exponential minus alpha r. So we know that the dispersion velocity in the radial part will be decaying exponentially. And the dispersion in Sept, it will be in terms of the density, the superficial density of the disk. And we have also this relationship. Then the dispersion in the azimuthal direction will be this one. So given the radial dispersion, we find the azimuthal, and with this relationship, this is the potential, the Newtonian potential. I derive the potential with respect to the r, and we found the angular speed, and with this angular speed, we found the epicyclic frequency, defined like this one, and with this one, with this expression, we have the velocity rotation given, for example, by obtained by observation, and the velocity dispersion in the radial part, the azimuthal, and the other parameters. So with all of these parameters, we can then know what is exactly this function, this Gaussian function. So given, again, three random numbers, I can construct with this distribution the velocities for the stars in the disk. And this is an example for using this procedure to construct a galaxy. Well, the disk of the galaxy. This is the H view and from the Sept view. And we can, given a galaxy, we can make, for example, a system of pair of galaxies interacting, just putting one in a certain distance of another one, and establish some parameters for the geometry of the collision. And we know for some galaxies proportion between the mass of the bulge, the mass of the disk, and mass of the halo, and play with the number of particles, the total number of particles in terms of them, and so on and so on. Okay, this is another part. So I will go quite fast, just to show you some objects in the universe. We have the sun, the moon, and cluster of galaxies, and this example is given in the book, and we will play with this example. The basic thing we have to know about this is to find the dispersion of velocities, to find the potential given the density, and as a test, try to find the virial condition, that the two times the kinetic energy and the potential energy is equal to 0. As a test, or to see that we have a virialized system, for example, or as a test for numerical issues. Then we have Andromeda, a lot of galaxies, nebulas, cluster of galaxies, planets, and we also have a cluster of galaxies, and observation in the biggest scale to see how galaxies are structured in the universe. We have these catalogs, the CFA catalog. We have more galaxies in the catalogs, and so on and so on. This is the scheme to make these catalogs, just to avoid the Milky Way plane. And we have also these catalogs to see how galaxies structure in the universe. And we have given an initial condition to see how we can model such kind of observation. I mean, to see how we can model this structure in the universe, how we can model how galaxies are getting together and making this kind of structure. So this is a simulation, and to do a similar observation like this one, we have to to establish a point of observation and then make the classification or establish, for example, given a point from here, we can test or observe around the halos formed around a given point of observation. And this simulation was basically done with just the second law, the Newton's second law, and this force. And this is one of the biggest simulations, which use 10 billion particles, and it takes like a month in one of the biggest clusters in that time to do the simulation. Was 25 terabytes of data, the evolution of history of 20 million galaxies, the cubic region of the simulation, or the simulation box was 500 megaparsecs, and so on and so on. The cosmology was the standard model for, I mean the lambda CDN model, and use a particular method to find the force. So given an observation like this one, how can we analyze or know something about these clusters of galaxies, for example? And the best way to understand is in the liquid case, for example, we have here a piece of a liquid, and we have molecules moving around, and we have that we don't have just seeing a snapshot. We don't have we don't see a specific pattern of the movement or of how they are clustering and so on. So to study this kind of a structure, we can do the following. For example, pick a particle, this one, the blue one, for example, and surround this particle in this case in 2-dimension spherical regions, and count how many particles are around in this region around the blue one. For example, in this case we have 1, 2, 3, 4, 5. And then go to the next radius. I increase the radius and construct another cycle, and then count how many particles are in this case. Okay, and so on and so on and so on. Then and keep that numbers or that histogram in mind, or I save in the memory or put in the disk. Then pick another one and do the same thing, and pick another one and do the same thing. And then we average the histograms. And with this exercise, what we get is this distribution. And then we don't have a specific pattern, or it's very difficult to see a pattern here, but when we make this calculation, we see something. For example, given a particle, he has a radius, or two particles cannot be so close together, because there is a repulsion in the case of molecules. So at the excluding this volume for each particle, we don't have nothing. We don't have, or there is not allowed, this region is not allowed for the particles. So we don't have no particles here, but then we have some particles surrounding each particle. And then we have another peak, so we have another region with more particles, then less particles, more particles, and so on and so on. This is the liquid case, and we have varying the temperature, for example, from a lowest value, 0.1, for example, in cold units, and to a biggest value of the temperature. So the kinetic energy dominates the potential energy, and what we see This one is, okay, this one is the, I think it's to the contrary. And when we have a lot of peaks, we have the solid state, and we have, in the intermediate case, the liquid state, and when we almost see only one peak, and then nothing, we have the gaseous state. So it's the same in the universe. So when we make a simulation like this one, we focus on a cluster and make something similar, but in this case I am interested in to find how is the matter surrounding this object, for example. And what they found is that the profile is this one, the NFW density profile. But also we can make similar analysis like I showed you before, but it's called the two-point correlation function. So, okay. And the most important thing is that observation, the blue one, corresponds statistically with the simulations. And we can play with the contents of the simulation box of the system, put more particles, less particles, and so on, or increase the gravity, for example, the gravitational constant, diminish the gravitational constant, and increase for example, the cosmological constant, and play around with all these parameters of the model, and we can find that if we add a lot of matter, we have very clumping structure. With less, we have this example, and with just, I mean, the lambda CDM model, we have the corresponding between observations and simulation. Again, so we have how come, this is one of the ways to find some information of the system, the NFW shift density profile, but we can also make analysis similar to the one I showed you before. And with this analysis, we can have the correlation function. How, what's the probability that given a galaxy in some point in space, we have another galaxies at some distance of the first one, for example. And this is the simulation 2 case. Is basically the same amount of data, but the simulation Q was less one, five times less than the Millennium 1. So the Millennium Simulation 1 was 500, and Millennium Simulation 2 was 100 megaparsecs. And okay, this is the Horizon simulation. This is the Millennium 2, Millennium 1, and this is the Horizon. The Q is really big. They use 6 gigaparsecs with a lot of particles, 69 billion particles. And they try to find specifically the correlation function and to see the BAO bump, which tell us that the two galaxies like to be at this distance, or separated this distance, which is around 100 megaparsecs more or less. And this is another simulation, the Illustris. Basically it's the same, but the hydrodynamic part of the code was improved in order to see star formation, nova recombination, and so on. A lot of details. So this is just to see something about general relativity, because the universe should be a model with the Einstein equation, so we have to make or to tell something about the general relativity. So this is the equivalence principle, and this is the way Einstein construct the Einstein equation, and this was the way Hilbert made the same. As I said before, these field equations are equations for the metrics. And this is some examples of the succeed of or prediction of general relativity. We have also, as I told you before, the cluster galaxies, and the main observation that give us the dark matter, about the existence of dark matter. So we have that to explain the rotation curve we observe in the universe. We have to measure how galaxies rotate around the center, and we have the stars rotate around the center of the galaxy, and we see this data. And we have to explain this data with the Newtonian physics, for example. So given the stars in the disk with some density profile, and given the gas with some density profile, we can find the rotation velocity contribution for the gas and for the stars. And combining these two observations, we don't have, or we cannot explain the rotation curve, so we have to add another density profile with some unknown matter and fixed parameters in order to fit the rotation and data. And this is the concept of the Doppler effect. Of course, this is only valid for the nearby galaxies. Okay, supernovae, what give us is that relationship between velocity and distance is almost linear, which is the Hubble law. And also with this observation is very clear, give us that if galaxies are moving away from us, then the universe should have or have to have or should have born in accordance with the Big Bang model. And this model tells us that in the universe must be some kind of radiation, a relic radiation, that satisfy the Planck formula.
¿Por qué dice los burros tocan la flauta?
But, because they were testing for another reason, or testing this antenna for communication, and they found the noise in the background. And that was the Big Bang or the CMB signal. So it was a beginning, very dense beginning with high temperature, and using the Einstein equation, these two people construct a metric and find that the metric, that this metric has only one parameter, and the parameter is how the universe is, the space is changing in time, making bigger or less. Okay, this is just a cartoon, and this is the expansion of the universe in 3 times. So closer, then separated, and more separated. And the redshift, in this case, is not for Doppler effect, is for the expansion of the universe. So if we use, for example, the separation of two galaxies at some time, we have that this relationship in terms of the separation of galaxies in another time. For example, this could be the time 0, time 1, and time 2, for example, and then we have this relationship. And given that we accept the cosmological principle, then we have that the separation only depends on T, and this dependence is only in the expansion factor. If we make some derivative for this relationship, we have the Hubble relationship. So this is the concept of the redshift. And when the universe is expanding, we have that the wavelength of the radiation is growing. And another thing from simulation is that if we analyze a small piece of space, we have that clearly the cosmological principle is not valid, but when we increase the piece of the space, we have that in average we have the validity of the cosmological principle. And of course we have to take this into account. From Newtonian physics, I mean from just the conservation of energy, we can construct the Freeman equation, which is this one, in terms of the density of the species which we consider in this model. And this is an equation for the growing factor. And for the field law of thermodynamics, we can find another equation for the density. And with these two equations, we can solve the largest scale of the universe. But we need to consider the smallest scales when this Friedman equation is not valid. So all the information we have from observation from cluster galaxies, a catalog of galaxies, the CMB, the supernovae, the rotation curves, and so on and so on. All this that we give us the cosmological pi, where we have the Hubble constant, and at the present time is 68 kilometers per second per megaparsec, and a lot of information. The cosmological constant is 17, well, around 70% of the total cosmic inventarium, or the content of the universe. 24 is dark matter, and 5% is baryons. And this model has a lot of problems, in particular for the smallest scales. And we have a lot of models to try to understand dark matter, Machos, WIMPs, general relativity, FR theories, MON, and so on and so on. And satellites problem. For example, counting the nearest galaxies to the Milky Way, we have that the number of these galaxies is fewer than the given by the simulations or what is inferred from this density profile, and so on and so on. So we have a lot of models, and okay. How much time do you have? 20. Thank you. Okay. So now I'm going to enter to the numerical details, in particular about the installation of the numerical codes I give you in the page of the school. And this is I'm using Ubuntu. This is a new computer. Well, this is a virtual computer. It's Ubuntu 16. It has nothing, so it's just to show you how to make the installation. The network. Okay. So you have this package. These are the codes. So all the zip files are here. I assume they are in the documents under this folder. So the simple one is this one. And the instructions are here for Ubuntu 16. So they are a lot of steps. I am sorry for that, but it is better that you understand the hard way. Because when you are in the real world, you have to be by your own. So, sorry.
Sorry, this is real world.
Okay, so the first step is going to the home. The home is just given by that environment variable, cd home. Home is applied to each one. In my case, home is used as home slash mar. So I am here. This is home. In your case, your home is your home. So the first thing is to unpackage one of the zip files. Is here. Sorry, let me. Keyboard. Sorry. So this is the first steps, one of the first steps. So you also unpackage, and then go to the instruction. I unpackage just one. I could do the other ones. This is another one. This is another one. And just for now, this one. So I have this package unpackaged. Embody, model, plot 2D, analysis, well, gadget. I need gadget also. Well, some libraries that gadget needs. That's it. So next. Okay. In the folder that was created by this method, so we have this folder, where is the system put, or the files for the system are put. So the first thing is to see any file that can be read. So this is the installation details. Okay, and this file is here. So the first thing is to move, unpackage and so on, to move to the NACBody directory and try and make some useful or needed directories that we need to have. So there are a bin directory created, a man directory, and zip, and a second man, and the local directory. In bin directory will be the binary codes. Next, change to the home. I mean, at this moment I'm in a level under my home, right? So go to the home is just writing this instruction. Then with the A, we need to use to the 8th because there are hidden files in your system, in your home, that configure or prepare your system to behave in a particular way. So you have to see in particular this file, and should be another, this one. And there is a lot of, this is a script that when you open a terminal, something happen and prepare the system to work in a particular case. In particular, all these scripts give us this environment. And what is important here is to see you can see, for example, that there are some variables defined. For example, when I invoke $home, I know, or the system knows that the home is this one. Is my own place in the hard disk. But there is another variable which is very important. This one, the path. This one, the path. So it doesn't matter where we are or where I am in the hierarchy of directories. I could be in the home or inside or very deep in some directory, and with this trajectory with this variable defined, we can find where the binary is. So given that I am pretending to put here the binaries for the numerical codes I will install, so I need to tell the system that no matter where I am in the system, I always can find some command or some numerical code. So I have to put this trajectory in the path, in the variable path. So the system have to know that the null body bin is here. Okay. So this is all the. So for Linux, for Mac, you should do this one. You have to do this one, or these commands. And for Linux, you have to do this one. So what I did was to add at the end of this environment script, to add these lines, which will define the environment to use in this system. So just check this, how is defined. So check the definition of the path. There is not a NAC body folder in any place here. And when I open a new terminal, the new definition enters. So I can run the same thing. And you notice that now we have this path. So we can find the binary codes whenever you are in the hierarchy of directories. So this is very important to have functionality in your system. What next? So change to the NACBody directory. And then make the installation of the first or the simplest code, which is this one. Okay. So in the binary folder we have the numerical code. Here, this one. And we can test it. Open a new terminal. We are in the home. We are here in the home. We make a directory to test. And we are inside this folder. So I will try to run, for example,
Mario, I have a question.
see?
I install everything what is called home, but not in my subdirectory as yours, Mart, but in home.
In your home is Jorge.
Yeah, but it's not, I didn't put things there, I put it in what is called home, not in Jorge.
No, but you are not allowed to do that.
I did. With sudo.
No, but no, forget sudo. No. No, it's,
So
no.
I followed your instructions. Go to home, I went home.
No, but home is home. Yeah?
Capital home?
No, it's capital home.
Yeah, I didn't know that.
No, it's capital home.
So what should I do now? Remove
That's the
that
home
and
is
begin
a
again?
definition of the path of where you put the things. It's not particular length at all. It depends on its use.
Exactly.
I got it now, but what should I do now? Because I
Forget about that folder and do it again. But with
Can you not rename
or just copy.
everything? Can you not rename whatever you call home to the specific one?
To move it to the other
Remove
place.
it? Can you not, once you put the files, can you not just change the name of the folder without having to move everything?
You can move the folder.
yeah, but they did as a sudo. No. So Jorge was doing this.
I believe this is a very specific question that we can answer. We can ask Mario at the break. I think we ran out of time. So, is there any general question that you would like to ask Mario?
We want to answer.
There's one over there. Yes.
Sorry?
Hello. So I was wondering when you were starting with the galactic one. So you mentioned about the genes equation, and you discussed the galactic simulation. So gene equation is for the static universe, right?
Static,
Yeah.
static system? No,
Yeah.
no. No? It depends on they involve a partial derivative with respect to time,
Okay. So
the general.
but the galactic simulation is depend on the genes equation.
What is the purpose of the gene equation, right?
Yes.
In this case, was to build initial conditions.
Okay.
O sea, you propose, for example, a spherical system, a density profile with a spherical symmetry. So you know what's the rho of R, and then you put in the gene equation to find the velocity dispersion. Then you find the Maxwellian distribution of velocities, which depend on the spatial part, of course. And then in each point in space, you can simulate or pick a random number from a uniform distribution, and then with the Gaussian, transform that number to Gaussian distribution and find a velocity for each particle. So just see, if you have 10 particles, do the same for each particle, and you are constructing the velocity part of the system.
Okay, so that equation is used to generate the initial condition.
The genes equation, but you can also use it for another purpose, of course. But in this case, to build initial condition.
And before that, you mentioned about interior and exterior. That is?
In the multiple expansion.
Yes. What was the difference?
The difference is the source and the you have an origin in the coordinate system. So it depends if you are looking for the potential at some inner part of a
Outside.
distribution.
Okay.
And is the other case when you have to see what is the potential outside a given distribution. So,
So it depends.
but the two parts come together in the expansion. We need both of them.
So it can be interior. Inside can be to represent the disks, and outside can represent. It is possible. It can represent the bulb.
Sorry,
In the one system like galaxy, interior can present the bulb part, and the exterior can present.
you need both of them
So, okay.
because it's the expansion of the green function.
Okay. No, I just.
So if I understand it correctly, that was the expansion of a term that was something like 1 divided by R minus another R.
In the multiple expansion,
Yeah, that was expansion, right?
are bigger and something like that.
Okay, so yeah, no, it's thanks.
I guess we can postpone the questions for the coffee break. So we'll have 20 minutes coffee break, and if you have particular questions to ask Mario during this time, please do. So we'll reconvene in 20 minutes.
Qué relajo.
Así que desconectas. No, aquí, solo cambiarle a mute.